Hi and welcome back to my Physics Online Video Lecture Supplement series. Today's video is the second part of the lecture on electromagnetic waves. And so in the first part, you were all introduced to electromagnetic waves in general. For example, we talked about the problem of displacement current, basically how Maxwell solved the problem of where is the current between two plates of a capacitor, and how with that formulation he then essentially was able to write out the Gauss's law for electricity and magnetism, Ampere's law, and Faraday's law, and how collectively with his solution added to Ampere's law these predicted electromagnetic waves. So in this lecture, I wanted to examine a few of the properties of electromagnetic waves. Now, we've already looked a little bit at stuff like speed of propagation and how the electric and the magnetic fields are related to each other. But we haven't really looked at anything like what kind of energy are they going to be carrying, what kind of intensity does an electromagnetic wave have, what's the spectral range, how do you produce them, this kind of thing. So that's what today's lecture is going to be. So let's start off actually with the end of that list, which is how do you produce electromagnetic waves. Now there's a variety of ways of producing electromagnetic waves. Basically, if you have an accelerating charge, you tend to produce electromagnetic waves. Why is that? Well, if you accelerate a charge, then not only do you have a changing electric field, you also would have a changing magnetic field. And those are the two things that you basically need in order to get electromagnetic waves. So there's a variety of ways to do this. As I've said before, the sort of first way to do that is to build an antenna. And at the end of today's lecture, I'll talk about electromagnetic spectra and some other sources of electromagnetic radiation. But you can think of this as something that is absorbed by and ultimately emitted by charges as they accelerate. And so if you can find a way to cause a charge to accelerate, then you can find a way to produce an electromagnetic wave. And so the antenna, which is actually pictured here, is maybe the simplest way to do that, and perhaps is the oldest way to do that in a controlled manner. And what this antenna is showing is what's called a half-wave antenna, sometimes also called a dipole antenna, because the E-field lines from this sort of resemble the E-field lines you'd get for a dipole. Basically, you'll recall that a dipole consists of a positive charge and an equal magnitude negative charge that are separated in space. So this is sort of like the positive, and this is sort of like the negative charge. They may be a little bit extended, however, as compared to the typical dipole configuration. So how does this thing work? Well, you start off with a pair of conducting rods. And so let's consider first of all the simplest case, in which you have two conducting rods as shown here, and then a battery with a switch that you can throw. If you close the switch, what's going to happen? Well, you can have some charges flow into the two rods. And so these two rods end up being oppositely charged, and therefore you get a series of electric fields that look something like this. And because you have current flowing, you also get a series of magnetic fields that look something like this. And again, you can get the magnetic fields by using the right-hand rule. Point your thumb in the direction of the current, your fingers will point in the direction of the magnetic field. So on this side right here, the magnetic field is down, here it's up, and everywhere in between it sort of makes a loop around this pole and a loop around this pole. Okay, so these fields do not appear everywhere instantaneously in space. In the static case, you could have the E field extending everywhere indefinitely, but in the static case, you also do not have a magnetic field. Furthermore, when you first place a charge here, if the charge were to sort of come into being right here, then you would initially have no electric field out here. It takes some amount of time for the information to propagate from this charge to some position out here. And so sometime later you get an electric field here, and then sometime later you get an electric field out here, and so on. And this is basically because there's a limit to how quickly energy can propagate. It's basically ultimately going to be the speed at which these electromagnetic waves propagate. Basically, energy is not going to be transported instantaneously from here, say, to here. It takes some amount of time for that to occur. And before moving on to the next slide, it's worth noting, if you look at this diagram, you have your E field, which looks very much like a sort of extended dipole E field. You have your B field, and the two are actually perpendicular to each other everywhere that the two exist. So now let's consider what happens if we remove the battery that we had in this previous setup and instead replace it with an AC source. So the AC source basically means that initially you might have, for example, the electrons move this way and the positive holes move this way, and then sometime later they will sort of switch. So the current basically kind of flows back and forth sinusoidally. And so we'll take that the voltage from the AC source has delta V naught, its maximum value. And so at that point in time, the E field strength in the antenna should be maximized. So if delta V is at a maximum, that's also equivalent to having all of the positive holes at one end, all of the negative charges at the other end. And so you have the maximum charge separation, meaning the maximum amount of charges and then some distance between them. And as you know, the electric field strength is going to be the potential difference divided by the distance if it's a uniform field. It would be sort of the derivative dV dx otherwise, or dV dz if you want to call this the z-axis. Okay, and the charges end up moving basically along this field line in the antenna. So at this point in time you're sort of at a maximum. A little while later the voltage starts dropping, and that means also that some of these charges start moving. And so you lose some holes here, you lose some electrons here. And eventually you have almost a neutral value, and at that point you have zero voltage, and then the voltage flips to the other direction, and so on. So this right here, this blue line, basically shows what the E field looks like within this rod. And as time passes, the E field basically goes to zero, and then it flips directions. Well, if you happen to be right here in the rod, then you sense this as it's happening. But if you were to place some sensor some distance away from the rod, it takes a little bit of time for these to propagate. And so basically what happens is that as these things propagate, you get a sort of sine wave in what you detect for your E field out here. Basically, the voltage looks like the maximum voltage times the sine of the angular frequency, that's 2 pi over period times the time. And so this is your sinusoidal voltage value. This is what you will also end up detecting for your E field, because your E field is basically this divided by some length of the antenna, for example. So what this does is basically you go through cycles where you have a maximum and then you have a zero and then you have a maximum the other way and then you have a zero and so on. So if you look down here at the time scales, t equals 0, this is 1/4 of a cycle later, this is half a cycle later, and we've gone from max to min. And then another quarter of a cycle will be back to 0, and another quarter of a cycle will be back to a maximum once again. And then the process just keeps on repeating so long as you have something to drive it. So that's basically what the E field is doing. Now let's consider what the B field does. So the E field during all of this is actually going to be sort of propagating away. In other words, if you have a sensor over here at 1/2 of the wavelength away from the antenna, then at time t equals big T over 2, in other words half a cycle later, you'll finally detect the maximum E field. And then after another half cycle you detect the maximum E field in the other direction. Another quarter cycle from there you're back at 0. But this is all delayed in time with respect to what you detect here at the antenna's location itself. So that's where you get the sine wave. This E field ends up being a function, therefore, both of time and of space. So with the B field, what ends up happening is that these charges move, sets up a current, and the current sets up a magnetic field according to Ampere's law. So if you have a current that's sort of upward, then by the right-hand rule you can see that your magnetic field is going to make a bunch of loops that would be I'd call them counterclockwise as looked at from above, where above this is the top and this is the bottom. So looking at it down from above, these are counterclockwise because the current is moving upward. And if you look at the E field everywhere and you look at the B field, you notice that they are always perpendicular. And that's true not only near the antenna itself or even inside the antenna, but as you propagate away from the antenna. So if you come out here, the E field is either pointing up or it's pointing down, and yet the B field is still in the XY plane. So E might be in the Z direction, B right here locally might be in, say, the Y direction. And so you have always a perpendicular B field to E field. And since the current is not constant, because again the current goes like the voltage divided by the resistance of these rods, you end up with a current that varies sinusoidally. And so that means that the magnetic field strength is also going to vary sinusoidally. And it's doing this at the same frequency at which the current is varying, which in turn is the same frequency at which the voltage is varying, which in turn is the same frequency at which the E field is varying. So that means that the B field and the E field vary with the same frequency. The wave will have the same wavelength for both of them, and they propagate at the same speed. Okay, so this means that you have both an electric field and a magnetic field that are sort of propagating outward. Now, the electric field lines reverse direction in time, and therefore they also reverse direction in space at a given point in time. And so what this means is that the electric field lines can ultimately form closed loops. So these red guys down here are basically the closed loops formed by the electric field lines. And so these E-field lines are actually propagating through vacuum in this case. There's no charges on which this E-field line can begin or end because it's in vacuum, and therefore it has to form basically a closed loop. I suppose the other option would be that it could basically come in from infinity and go out to infinity, but forming closed loops is a possibility as well. And in this case, they will form closed loops because of the geometry of the thing producing them. So these E fields and the B fields both change in time. And so what that does for us is it means that you get a wave that is actually self-sustaining even if the antenna stops operating. What does that mean though? It doesn't mean that you continue to produce more E-field waves when this stops. What it means is that the already produced waves will continue to propagate even after this stops. So this wave will just keep moving to the right off until it either collides with something and is absorbed or reaches infinity. So that is the production of electromagnetic waves, or a simple version of the production of electromagnetic waves. What about the energy that is actually contained in these electromagnetic waves? Well, we previously looked at energy density for two things. On the one hand, for an electric field, and on the other hand, for a magnetic field. We did this in the context of a pair of parallel plates, in other words, a capacitor, and in the context of a coiled wire, in other words, an inductor. And basically, what we found is that for a capacitor, the energy density was 1/2 epsilon naught times the E field strength squared. And in the inductor, it was 1/2 of the B field strength squared divided by the permeability of free space. So the total energy density, if you have somehow both a capacitor and an inductor, would be the sum of these two terms. Well, it turns out that that's basically how you get the electric density, the energy density, for a traveling electromagnetic wave. Again, energy density is total energy divided by volume. And in the previous part of this lecture set, we found that the E field divided by the B field gives c, which is the speed at which the electromagnetic wave is propagating. So that means that this energy density can be obtained in terms only of E or only of B. And the reason why that is because this right here, 1/2 epsilon naught E squared, could be rewritten as 1/2 epsilon naught times B times C quantity squared. So now you have this in terms of B and this in terms of B. And similarly, you could, instead of substituting out E for B, you could substitute the B for an E, because B is going to be E over C. So basically what that does is that you can get this energy density to be either epsilon naught E squared, or you can get it to be B squared over mu naught, or alternatively square root epsilon naught over mu naught times E times B. And again, this is because recall that we found that the speed at which these propagate goes like 1 over the square root of epsilon naught times mu naught. So that's where these substitutions are coming in. So I wanted to talk now about how much energy is being transported by an electromagnetic wave. And electromagnetic waves, it turns out, are going to be transporting energy. That follows from the fact that we have an energy density for an electromagnetic wave, which is what we found on this previous slide. So if you multiply that density times the volume, you've got a total energy. And I'm not going to go into too much detail about how much energy an individual wave packet is carrying. An individual wave packet is sometimes called a photon. And I don't want to talk too much or get too much off track talking about photons, but basically they are a wave packet. They behave kind of like a wave, but they also can behave kind of like a particle. So there is sort of a particle wave duality to electromagnetic radiation in the form of individual photons or individual wave packets. Um, it turns out that how much energy an individual photon is trying to carry is determined by the wavelength of that photon, and then another fundamental constant of the universe called the Planck's constant. But I don't want to belabor that particular point. If you want to find out more about that, then you'll learn about it if you take a modern physics class, and then again you might see it some more in upper level physics courses. So setting that aside, how can we consider the amount of energy transported by a actual wave of electromagnetic radiation, a sort of continuous wave, if you will, rather than an individual photon? Well, the way that we do that is we consider a surface of area A, and that surface of area A is the surface through which the electromagnetic wave is going to pass. And we'll consider the electromagnetic wave to sort of fill that surface A. So this wave is traveling at a speed of c. That's the speed of electromagnetic radiation, 2.9979 etc. times 10 to the 8 meters per second. So if you want to know how far the wave travels in an amount of time t, you'd multiply the speed c times t. So if you want to consider that over a very short time dt, then you get a distance dx is c dt. Now, in this short amount of time dt, the volume will have passed through a total volume of dv. And dv is obtained simply by noting that the wave is filling an area A and it's traveled the distance dx. So dv is a dx. And so because dx is c dt, that means that dv is ac dt. All right. Well, that gets you the infinitesimal volume. How much energy is there within that infinitesimal volume? Well, it must be the energy density times the volume, because that's how energy density is defined. Energy is energy density times volume, or more properly, energy density is defined as energy per unit volume. So the infinitesimal amount of energy contained in this infinitesimal volume must be du equals u dv. That's true by definition, and since dv is ac dt, du must be uac dt. So that gets us a general idea of how you obtain the amount of energy within a wave. You basically then have to integrate over time to find this total energy. This quantity, by the way, that we find up here is actually sort of analogous to what's called fluence. Fluence is basically how much energy per unit area does the wave carry, and it's related to intensity. Intensity is how much energy per unit area per unit time, or how much power per unit area. Recall that we defined that when discussing mechanical waves, so it's true for waves in general. So basically fluence, therefore, is the integral of intensity with respect to time. So the fluence would be du over A. The energy is just du. So here is a better picture of what all that looks like. Here is your surface with area A. Here is your electromagnetic wave that is impinging upon the surface and really fluxing through it. And the volume of the surface, dV, is A dx, is going to contain some energy du. And if you want to get the total energy for the wave, let's say for one cycle of the wave, then you'd need to integrate over the entire period of one wave. So the entire period would be the amount of time that it takes to get through this whole regime in which there are electric field and magnetic field arrows shown. Of course, the wave can continue thereafter. But there's actually another thing of interest, which is called the Poynting Vector, sometimes represented by a capital S. And this is often used to describe how much energy is being transported by an electromagnetic wave. Basically, the magnitude of the vector is actually the intensity. It's the amount of energy transported per unit area per unit time by the electromagnetic wave. So, of course, it's going to have units of joules per second meter squared or watts per meter squared. Well, S basically is the energy per unit area per unit time. Therefore, S is 1 over A du dt. And so again, if you integrate S over the long amount of time, or over even a short amount of time, but represents an entire cycle of the wave, then you get the fluence contained within a wave. If you then divide out the area that fluence is falling, or multiply by the area that fluence is falling on, you get the energy in the wave. Well, 1 over A is going to be, or 1 over A times du dt is going to be epsilon naught c times E squared, and thanks to the relationship that we have between E and B, that can also be EB over mu naught. So basically this gives the magnitude of the Poynting vector, or the magnitude of the intensity of this wave. It turns out that what the Poynting vector itself is, because that was a magnitude, we're talking a vector here. It turns out that the Poynting vector itself can be given by taking a cross product. The Poynting vector is 1 over mu naught E cross B. So that is how you get the actual vector, Poynting vector. So what direction is the Poynting vector in? Well, E and B are perpendicular to each other, and they're both perpendicular to the direction in which the field propagates. So this would either give us the direction that it propagates in, or the opposite of the direction that it propagates in. It turns out that because of the order chosen, E cross B, that this is going to give us the direction in which the wave propagates. So the whole vector is basically how much energy pointing along the direction that this wave is propagating in. So if you want to find the intensity, therefore, you find the magnitude of the Poynting vector, and that basically looks something like E of t times B of t over the permeability. Now, E and B, we established earlier, both have functions that look like sine waves. They are waves, so they should have the form of a propagating wave, or a traveling wave. So it's not just E equals E max or E naught or whatever times sine of omega t. No, that's not true, because if you go away from the antenna where this is being produced, you can still get a wave. It's going to be offset by some kx factor. K is the wave number. So K, recall, is given by 2 pi divided by the wavelength. And so this right here is the form that the E field will take. This right here is the form that the B field takes. And you'll notice that in both cases you have sine kx minus omega t, so they're in phase with each other. That means that you can find the instantaneous intensity by basically just squaring the maximum electric field and then squaring the sign of this argument, kx minus omega t. This is, of course, called the phase of the wave. And if you want to get the average magnitude, then you are going to get the time averaged intensity, which is, if you refer back to your notes on AC circuits, it's going to be given by the root mean squared electric field and magnetic field. So recall that when we wanted to find how much power was being used in an AC circuit, we still multiplied the current times the voltage. Then we noted that both current and voltage had a sine function. They were both I naught sine omega t and V naught sine omega t. That therefore we could write it as, for example, V naught squared sine squared omega t over R. And so what we did was we defined a root mean squared voltage and a root mean squared current. Well, the same thing works here for E field and B field. You can have a root mean squared E and a root mean squared B. They are, in fact, obtained in much the same way as with the current and voltage. In other words, root mean square for the E field is going to be whatever the maximum field strength is divided by square root of 2. The B field root mean square is whatever the maximum B field is divided by square root 2. And of course, again, you can make substitutions between these two to get from E to B and vice versa. Now, electric fields and magnetic fields in the form of electromagnetic radiation not only carry energy, but also momentum. And basically what this means is that if you have electromagnetic waves which are incident upon a given object, these waves can either be absorbed or reflected. And in being absorbed or reflected, they will transfer some momentum to the object. If an electromagnetic wave is carrying momentum and it's reflected, then it's going to behave very much in the same way as far as transferring momentum goes as a ball which hits an object and then bounces off. So here's your electromagnetic wave. It hits an object, it reflects off the object. Here is a ball, it hits an object, it reflects off the object. The momentum has been changed, therefore some momentum is transferred to this object. Now, again, without getting too far off topic, the way that this is handled with electromagnetic waves is they hit the object and they deflect. And if the object is initially stationary, then the wave simply deflects and there's no change other than that its direction basically reverses. Or it can come in and deflect by bouncing at some angle. In those cases, there's no real change to the wave's properties. It turns out, however, that there is something more that can be done, because you can have a ball that hits something like a wall or whatever that's initially stationary, but you can also have a ball that hits a baseball bat, which is swinging towards it. Or you can have a car that rear ends another car that's already in motion. And in these cases, you get something a little bit different than what you would have had if you just simply crashed into a stationary object and deflected. For example, when the baseball hits the moving baseball bat, it doesn't deflect at the same speed that it enters in, but rather often deflects at a much greater speed. Hence, you can hit a home run. Well, the equivalent thing that happens with photons is that they undergo what's called a Doppler shift. And that basically means that their frequency ends up changing. And so the amount of energy and momentum carried by that photon will also therefore shift. In any case, what happens in the simple case where you have a stationary object and then the photon hits it and then is reflected, is that you're going to have to conserve momentum. So if you had initially p in this direction, you're going to deflect with p in the opposite direction, and you have to give 2p to the object that you are reflecting from. And so the change in momentum ends up looking like 2 times the change in energy over c, where change in energy is the change in the object, in the photon's energy. And this basically ends up looking very much analogous to the case not just of a ball colliding with some object, but with a ball colliding with a much larger object. So it's a perfectly elastic collision between, say, a ball and a wall rather than between two balls. So in other words, the change in momentum is 2 delta U over c if your photon is reflected. Your other possibility is that the photon can be absorbed. And if the photon is being absorbed, then the momentum of the photon goes away as far as the photon is concerned, but overall momentum has to be conserved. Basically, that means that it transfers all of its momentum to the object that is absorbing it, and so the object will pick up a total momentum. Delta P is equal to delta U over C. Delta U is the energy that the photon had. It's effectively absorbed. So whatever energy was in this photon is divided by C, gives how much momentum the photon had. That gives you how much momentum the wall has. Now, to see why delta P could be twice as big when reflected, you can imagine that you have two things happening here. First of all, you have a photon incident on the object. It hits the object and is absorbed, and so you get 1p. Then, for a reflected thing, the photon is re-emitted in the opposite direction. So that is another delta p's worth given to this object in this direction. In any case, the absorbed case is somewhat analogous to the case of a very small object colliding perfectly inelastically with a large object. The two stick together. It's even more perfectly analogous to the case where your small object collides with your large object and the small object comes to a stop. So whatever the large object is doing, the small object has come to a stop as a result. That is total absorption. Now, if electromagnetic radiation is going to transfer momentum, then by Newton's laws, it basically has to be applying some sort of a force. So the photon applies a force to the wall. All right, well, force, you'll recall, is dp dt. And so that means that you can obtain the amount of force applied by the electromagnetic radiation by first figuring out what the rate at which this momentum transfers are happening. So the momentum transfer is delta p. If you know how much time delta p takes, then you have the rate at which it is being transferred. And if you do that over a short amount of time, you've got dt, which is the force. So force, in turn, can be rather small when we're talking about individual photons. And so one way of measuring force for photons, or for that matter for any kind of fluid that is incident on an object, is to measure the pressure exerted. So pressure is force per unit area. We've had fluence, which is energy per unit area. Now we have pressure, which is force per unit area. So you can kind of guess at what the relationship between fluence and pressure is, but for our purposes, pressure is 1 over the area times the force, or times dp dt. So now we can put all that stuff together, and what you end up getting is that the momentum carried by a wave is going to be related to the energy carried by the wave, P equals U over C. So if you have the wave being absorbed, then delta P equals P, and therefore the pressure is 1 over the area times du dt divided by C. And so that's 1 over AC du dt, and that is, of course, the average of the Poynting vector, the average magnitude of the Poynting vector, divided by C. And then if the electromagnetic wave is reflected, then the transferred momentum is twice as great, and so the pressure is 2 times the average Poynting vector over C. So these are sort of average pressures in time. I suppose you could get an instantaneous pressure as well by just using the Poynting vector and dividing it by C. The instantaneous Poynting vector is magnitude. I earlier alluded to the fact that when you have a collision between a photon and matter, if the matter is initially moving and if the photon is reflected, that the result is that you get a shift in the frequency of the photon. Well, I want now to consider the frequencies of photon in general, because the frequency and the wavelength give us what's called the electromagnetic spectrum. And basically what it means is that the fact that they can be shifted in frequency already implies that EM waves can span over some spectrum of wavelengths and frequencies. And you could, when we were talking about antennas, see how that's possible by noting that it's possible to have different frequencies of AC sources. In other words, it's possible to have a different frequency at which an AC source is driven. And so that already implies some range of frequencies for which you can drive electromagnetic radiation. It turns out that the electromagnetic spectrum is actually quite broad. In fact, it's a bit broader than what you can get just from using an antenna. And so there ends up, therefore, being other sources of electromagnetic radiation beyond just the electronically driven antenna shown earlier, the dipole antenna. And I should say here that the frequency and the wavelength are related, as with any other waves, by C equals lambda times F. And what I'm showing here is sort of a standard chart showing the electromagnetic spectrum. This is the frequency, this is the wavelength. These are in hertz, that's cycles per second. These are in meters. And you can see that there's sort of different regimes within the electromagnetic spectrum. You have the radio wave regime, you have microwaves, you have infrared, you have visible light, ultraviolet light, X-rays, gamma rays. And so I want to kind of look at a little bit of that in some more detail. As I said, these waves span quite a spectrum, or the electromagnetic waves span quite a spectrum of wavelength and frequency. And you can break it up into general types of electromagnetic radiation. They're often categorized by such things as how you produced them. For example, these radio waves that I described earlier with the antenna, like a 60 hertz signal, AC current is going to be a very, very, very low frequency, very, very long wavelength radio wave. But at some point it becomes difficult to drive a circuit, even an AC circuit, at a high enough frequency to produce larger and larger waves. And so you run from radio waves into, for example, microwaves, which have some other method of production. Then you get into infrared, which has yet a different method of production, and so on. And it's worth noting here that adjacent wave types often will overlap a bit in frequency and therefore in wavelength range. This is because, for example, we might be able to produce a very, very, very fast AC signal, very high frequency AC signal, which can be used then to generate a radio wave. And that same radio wave, a wave of the same wavelength could be generated by some other method, such as by sort of stretching and compressing a molecule, basically causing molecular vibration or rotation at a very low frequency of vibration or rotation for a molecule. And so we might say that one of those is a microwave because it was produced by rotating a molecule, or by adding rotational energy or taking rotational energy away from, ultimately taking rotational energy away from a molecule. And yet it has the same wavelength as another wave that was produced by a conventional circuit that's trying to drive an AC signal. So there ends up being some overlap in wavelengths as a result. So you can see that the shortest wavelength, highest frequency radio waves overlap somewhat with microwaves that are on the long end and low frequency end. And similarly, microwaves have some overlap with infrared. The exception to this overlap thing is that infrared, visible, and ultraviolet are well defined with respect to each other as far as the visible light goes. And the reason why that is because visible light is basically just defined as the spectrum of the electromagnetic waves that we can actually see. So there's nothing special about visible light as far as how it's being produced, but we tend to give it its own category because it's the only thing of all this that we can look at with our eyes and actually see. So there is actually a reasonable boundary between infrared and visible, and between visible and ultraviolet. And part of that is basically because visible is just a very small spectral band that we happen to be able to see. You produce it in the same way basically as infrared or ultraviolet, and it sort of ends up forming the border between the two. You could argue that if we classify things solely by how they're produced, that in fact infrared and ultraviolet would overlap. The reason why we don't is because we have a nice, sharp, easy to define boundary between them, given by what we actually see. So let's look at each of these types of electromagnetic wave, not in a lot of depth, but kind of in passing. We'll start with the low energy waves, which basically means low frequency and long wavelength, which would be radio waves. So these are the waves that have wavelengths that are kilometers long down to maybe a tenth of a meter in length. And the main thing about radio waves is their production is usually by using either an LC oscillator or an antenna or both. In fact, usually it's a LC oscillator that's driving an antenna. So these are sort of electronically produced using, for lack of a better word, electrical circuits. And they are obviously quite useful to us. They're used in basically most of our telecommunications devices, radio, TV, Bluetooth, Wi-Fi, cell phones, all of these things, and then MRI machines all use radio waves. Now, the TV, Bluetooth, Wi-Fi, and cell phones actually are using wavelengths that are kind of near to the microwave band. If we scroll up a couple slides, you can actually see them listed on here. Here's your AM radio. It's clearly in the radio band. Here's your television. These would be sort of like the old antenna televisions. So channels 2 through 6, channels 8 7, 8, 9, 10, 11, 12, whatever channels you used to be able to tune through when you had the old 12 channel television set that hooked up to a literal antenna. Um, these are actually already starting to poke into the microwave wavelength. Your cell phones actually operate at two different bands. One is actually more clearly in the microwave, and one is more clearly in the radio. And satellite TV is, in fact, in the microwave range. A lot of your Bluetooth devices also fall in this range. It's worth noting with these that the radio waves are more highly regulated as far as what you're allowed to produce on a large scale, simply because of how important they are for a lot of communication, telecommunication, even cell phone, and so on. So there's sort of strict regulations on what you're allowed to produce and what radio waves are allowed to be used for what kind of operation. There's also extremely low frequency waves, and these are used if you want to communicate with submarines that are submerged underwater. And the reason for that is that water tends not to absorb these extremely low frequency waves. It might absorb some slightly higher frequency waves like in a conventional radio. Okay, moving along the spectrum, we get to microwaves. So these are in the wavelength range of maybe 0.3, even like 0.1, or even slightly shorter wavelength, slightly longer wavelength, all the way down to 10 to the minus 4 meters. So 0.3 meters, notice, is slightly longer than the wavelength that was sort of the minimum wavelength in the radio frequency. So radio frequency and microwave overlap. They overlap wavelength-wise between about 0.3 meters and 0.1 meters. And so here's what the frequency equivalents for microwaves are. Notice 100 megahertz is actually within your FM radio. If you look on the FM dial of your radio, if you're using an AM FM radio, the AM stations often come with some big number. It's in the thousands. Well, those thousands are actually kilohertz. The FM stations seem like they come with a smaller number. They're actually megahertz. So if you turn your dial on your radio to 101 or whatever, 101.1, then you're tuned to the frequency of 101.1 megahertz. So that is in the radio frequency, just barely. It's also just barely within the microwave frequency range. And how do you produce a microwave? Well, you use thermal agitation. It's of the vibrational and rotational modes of molecules. And so basically that also means that they can be absorbed readily by a vibrating or rotating molecule. Basically means it'll kick up the energy of vibration or rotation by another level when one photon at this frequency is absorbed. So one very big use, obviously, of microwaves is heating. Most people now have a microwave oven, and it basically is used to heat the molecules in your food by basically causing them to rotate, and then that rotation ends up causing collisions, which then cause vibration, which actually is what heats your food up. Another thing that microwave is used for is radars. In fact, if you talk to some sort of old timers, they will often call their microwave ovens a radar range. So radar, though, used for detection of whatever aircraft, or if you're on the ocean, maybe it's used to detect other ships, etc. These are actually in the microwave range. And then cell phones, I mentioned before, up here for radio wave usage, 800 megahertz band. The other band that cell phones commonly use right now is the 1900 megahertz band. So cell phones actually use both the microwave type and the radio type of electromagnetic radiation. If you're watching satellite TV or digital TV, then you're also making use of microwaves. In fact, if we scroll up to that chart again, you can see that satellite TV actually sits more or less in the middle of the microwave range. And the other interesting thing is historically that the microwaves are what Hertz himself was actually able to produce, although he basically was kind of on the cusp between radio and microwave. Okay, next shortest or next longest wavelength, and therefore the next lowest frequency, is the infrared. And so these follow in the range of about 1 millimeter to 700 nanometers. Roughly 700 nanometers is as red as your vision will go. So notice this is lambda has to be greater than 10 to the minus 4. That's 0.1 meter. Here, 0.1 millimeter, excuse me. Here, lambda has to be less than 1 millimeter. So the range of overlap is from 0.1 millimeters to 1 millimeter. These ones also are produced by thermal agitations, but it's almost entirely molecular vibrations. There are also some outer shell electron transitions that fall into the infrared. So basically, if you have an atom and there is an electron which is in the n equals 5 shell and it falls to the n equals 4 shell, odds are it's going to be producing a photon in the infrared range. Again, you can also get this from thermal agitations, mostly molecular vibrations. So here you have, for example, the stretch mode of a water molecule. And if you have some stretching, some asymmetric stretching or some symmetric stretching either way, and you excite those stretches so that they stretch more, then it's going to produce, it's really going to absorb some radiation at this frequency. And if the molecule is basically slowed somewhat from how much it's stretching, if the stretch is reduced, then it's going to emit some radiation at this wavelength. And this stuff is actually associated a lot with vibrational and even translational energy of objects, that is, with temperature. So if you have a pair of IR goggles, then you can see what looks like heat vision, if you will. So here's sort of a blow dryer that is releasing a cloud of hot air. You put on your infrared goggles and it looks like, wow, there's a lot of hot stuff here. It's kind of cooler over here. So you can heat image using infrared. The other interesting thing about infrared is that it is the primary sort of band that is responsible for heating the Earth, like sort of heating the Earth's atmosphere. This is true as far as global warming goes. The thing that really causes global warming is you get solar radiation, it impinges on the atmosphere. Basically, some of the visible and ultraviolet light is going to reflect from the upper atmosphere. When this hits the Earth, it reflects off the Earth and there is a frequency shift. And that frequency shift is explainable again as a sort of Doppler shift as it reflects off the Earth. Basically, the Earth is moving, not stationary, and therefore you can expect a frequency shift in the light. Well, if the frequency shift is to infrared, then it hits the atmosphere and basically is going to bounce off the atmosphere, hits the Earth, gets absorbed a little more, bounces off the atmosphere again, hits the Earth, warms up a little more, uh, uh, shifts a little more. And the longer the wavelength is, the harder it is for it to uh, basically escape the atmosphere. So very long wavelengths tend to bounce off of the atmospheric layers and therefore get trapped on, between the atmosphere and the Earth. And each time that they collide with the Earth, they heat the Earth up just a little more. And so that's where you get global warming from. Visible light, on the other hand, tends to pass through the atmosphere fairly readily. It's basically transparent to visible, and actually the ozone layer tends to reflect a lot of the ultraviolet, so the ultraviolet often doesn't really make it all the way through anyway. Some does, obviously, because you have to wear like ultraviolet protection and so on when you're out on a sunny day, but a lot of it's sort of deflected by the ozone layer. So now the next part of the spectrum is what's called the visible spectrum. And these ones are often produced by electronic transitions in atoms. Basically, the Balmer series in hydrogen will produce it. So here's the Balmer series transitions for hydrogen. Balmer series basically means that it's going from an outer shell down to the n equals 2 shell within an atom. And basically when that happens, the electron emits a photon, and that photon has energy that's equal to the difference in energy levels from where it started to where it ended. So the higher out it is, the greater the energy change, and therefore the greater the energy the photon, hence the shorter the wavelength. So an n equals 6 to n equals 2 transition would start here at the n equals 6, it'd fall down to the n equals 2. It releases wavelength about 410 nanometers. N equals 3 to n equals 2, only about 656 nanometers, and so on. So quite a few different atoms, in fact, I think just about all atoms, will have some transition or other that produces visible light. And in fact, you can see for iron, it produces a pretty substantial number of bands of visible light, whereas hydrogen actually produces 4. Basically, these 4 that are shown up here. So here's your 410 nanometer, here's your 434 nanometer, here's the 486 nanometer, here's the 656. That's what you're produced by hydrogen. Now, these atoms will produce plenty of bands that are not in the visible spectrum, but we're interested here just in seeing what visible light gets produced. And the answer is it's almost always produced, at least for smaller atoms, by a Balmer series transition. That means from n equals greater than 2 to n equals 2. This light obviously is important to us because it's what we see, so it's what we detect by our vision. It's also pretty important in photosynthesis. That's why plants often are green or have green foliage, is to absorb more of the green light. And so if you shorten the wavelength beyond violet, you get into ultraviolet. And so this is stuff it's actually maybe about 380 nanometers that you can see down to. So that's usually the actual cutoff, all the way down to about 0.6 nanometers. And so this is in the frequency range 750, should say, petahertz, terahertz down to about 5 exahertz. And these ones, just as with the visible, these ones are produced by electronic transitions inside of atoms. For example, they are often caused by transmission in transitions in to the n equals 1 level rather than to the n equals 2 level. Or if it's a very large atom, then it's actually not necessarily going to be an inner shell transition, but maybe it's to an n equals 2 or n equals 3 level for something large like, say, uranium. And it's good for quite a bit of stuff. It actually has a lot of different biomedical uses or applications. This right here, for example, is a laser that they use for laser-assisted angioplasty. So basically what happens is you get the plaque buildup within your veins or arteries, and you want to remove that plaque so that blood can actually flow through the vein or artery. And one way that you can do that is you can sort of use a little laser to burn out that plaque, basically just ablate it. Another thing it's used for, if you like to go camping, or especially if you like to go backpacking or backwoods camping, that kind of thing, it can be used to sterilize different surfaces, including sterilizing water to make it safe to drink. And also, UV light interacts with stuff like phosphor to make things glow in the dark. It can interact, for example, with a number of bugs, including especially like a scorpion. So if you go outside and you see a scorpion at night and you turn on a UV light, or you even look at the UV light that's reflecting off the moon, you might see that the scorpion kind of glows in the dark a little bit. And the other thing about it is that it not only causes sunburn, but also can be very harmful to your eyes. And it gets absorbed by the ozone layer. So if we flip back up here a little bit to this greenhouse gas thing, you get UV light off of the sun. It does make it to the earth, but a lot of it's being absorbed by this ozone layer. If you deplete the ozone layer, then you get more UV light making it to the surface, which obviously means a lot more sunburned people, but also more cataracts, maybe more cancer, and so on. Okay, after the UV, the next part of the spectrum is X-rays. And these ones actually can have wavelengths down to about a picometer. And what basically this does is it's produced by very far inner shell electronic transitions in large atoms. So for example, if you have uranium, let's say, and you have an electronic transition from n equals 2 to n equals 1 shell, odds are you're going to be producing, in fact, in that case, you are going to be producing an X-ray. For most large atoms, you can produce X-rays by transitioning to the n equals 1, in some cases even to the n equals 2 shells. And they are quite useful for, obviously, for medical diagnostics, but also because 0.1 nanometer falls within this range of wavelengths. They're also really useful for doing crystallography, because the typical separation between atoms within most solids, most crystalline solids, is about 0.1 nanometer. So these are very nice for studying crystal structure. Last but not least, you have gamma rays. So a gamma ray is basically everything else. It's everything at the very shortest wavelengths. I guess we must have detected stuff to less than 10 femtometers. What they're associated with are things like nuclear decays. So when you have a nuclear bomb explode, it releases a lot of radioactive particles, it also releases a lot of gamma ray radiation. It's also produced by matter-antimatter collisions, basically annihilation events. And you also can get them in cosmic rays. Like here's a supernova, it's going to produce cosmic rays, which are basically gamma rays. And of course, if we want to look in fiction, Bruce Banner became the Hulk because he was bombarded by gamma radiation. I think in reality, if you were bombarded by gamma radiation, you would basically just die. Is sort of how you die from the fireball of a nuclear bomb if you're close enough, assuming that you don't get destroyed by whatever the hell else happens. You have to shield from it by using very thick layers of lead. They are very penetrating, very damaging. They actually can easily rip apart any atom. Any electron in an atom can absorb it and be instantly ripped off the shell that it's orbiting. In fact, the very high energy ones can sort of rip apart nuclei. So that is all of the different types of electromagnetic radiation that we have. Alright, so now I would like to work through a few examples. So we'll start off with a couple examples of the energy and just basically the wave properties and energy transported by some wave. So let's say that we have a wave, an E&M wave, whose maximum electric field magnitude is 250 megavolts per meter. What we want to know is what's the RMS, E field, and B field strength of this wave. Well, from before I'd already written up here these pair of equations, and so For the E field strength, it should be basically Emax is given by the 250 megahertz, so 2.50 times 10 to the 8 volts per meter, and then that's divided by square root of 2. So what that gives us is basically going to be something like 1.767 times 10 to the 8. So maybe 1.77 times 10 to the 8 volts per meter. We now want to get the root mean squared for the B field. Remember that E over B is equal to C, and so that means that B can be obtained by using E divided by C. So that's true also for the RMS. So we could use E RMS over C. So we would basically go 1.77 times 10 to the 8 volts per meter divided by C, which is basically 3.00 times 10 to the 8 meters per second. And so the root mean squared for the B field is going to be roughly 0.589. So 0.589 Teslas. So we've got our B RMS, we've got our E RMS. Next example asks what the energy density for the above wave is. So if you want to find the average energy density, basically the energy density little u is given by epsilon naught times E squared, or you could use B squared over mu naught. So that's B squared over mu naught, and that's also square root of epsilon naught over mu naught times E times B. I'm just for simplicity going to go with this version right here. So the average energy density should be given by the epsilon naught times the E field squared. So that is epsilon naught times E squared. So E squared would be 1.77 squared, which is 3.13 times 10 to the 16, and then that's times another 8.854, and then that is times 10 to the minus 12. So what I end up coming up with is basically 27.7 times 10 to the 16 minus 12 would be 4, and that's joules per cubic meter. So if we want to put this in a little more proper of a scientific notation, maybe 2.77 times 10 to the 5th joules per cubic meter. Okay. Then it asks, what is the average and maximum magnitude of the Poynting vector for this wave? Well, we have that the magnitude of the Poynting vector S can be obtained by, for example, epsilon naught times C times E squared. So that's basically C times little u, because epsilon naught E squared gets us little u. So this right here, this one was for the average of little u. And so basically, if we want the average Poynting vector, we can use the average of little u times c. And so that's basically 3.00 times 10 to the 8 times this 2.77 by 10 to the 5th. And that is going to give us units of joules per meter cubed times meters per second squared, so that's joules per second dot meter squared. So basically what that gets us is something like average value for S is 8.3216 times 10 to the 13th power watts per meter squared. So that's your average intensity for this wave that has just been described. Now your maximum intensity you can obtain by using S max is equal to epsilon naught C times E max squared. So E max was 250 megavolts per meter. So this ends up being 8.854 times 10 to the minus 12 farad per meter times 3.00 times 10 to the 8 meters per second times 2.50 times 10 to the 8th volts per meter. So if we multiply all of those guys out, what we end up getting is about 16.6 times 10 to the 13, or 1.66 times 10 to the 14 watts per meter squared. Now, there's also a simpler way of doing it than going through this whole calculation, because remember that the root mean squared electric field is 1 over square root 2 times the maximum electric field. So this maximum Poynting vector should be twice the average Poynting vector. And in fact, you see that if you double this, you get roughly this, once you account for some round-off error. Next, we're asked if the wave's frequency is 150 terahertz, what is the instantaneous intensity of the wave 2 femtoseconds after the first E-field peak? Well, in general, S, the Poynting vector, is epsilon naught C times E max squared. Well, that means that the times E of t squared, I should say. That's basically going to be the same as epsilon naught C times E max times the sine of kx minus omega t squared. So you can pull some stuff out of here to get that S is equal to epsilon naught C E max squared. This would be the same as S max, or the maximum Poynting vector, times the sine squared of kx minus omega t. And we're basically just looking at so many seconds after the first peak. We were given that the frequency in this problem is 150 terahertz. So F equals 150 terahertz is the same as 1.50 times 10 to the 14 hertz. Omega is equal to 2 pi times F, and so what that basically is going to give us is about 10 times 10 to the 14 terahertz. In fact, it's 9.4245 or whatever. 9.42 times 10 to the 14 inverse seconds. Okay, and so we're asked at time t equals 2.0 femtoseconds, that's the same as 2.0 times 10 to the minus 15 seconds. After the first peak, what happens? Well, we can do some fancy trig work to get to that. Basically, you could say, suppose that kx equals 0, and so at what time are we going to get that first maximum? And the answer is going to be, it's going to be after 1/4 of a cycle. Well, instead of going through 1/4 of a cycle, we could instead replace the sine with a cosine. And so you effectively have cosine squared of omega t. And so basically this means that S is going to be S max times cosine squared of omega t at this particular place at this particular time. So that's just going to make it so we don't have to do a lot of extra calculation gymnastics to figure out what time this actually occurs at. We can just plug the 2 femtoseconds directly in here. So basically what we have is 9.42 times 10 to the 14 times 2 by 10 to the minus 15. So for all intents and purposes, that's 9.42 times 0.2. So if you multiply 9.42 by 0.2, you get 1.884. And so that is, of course, in radians. So if you take the cosine of that, what you end up getting is negative 0.309, which is fine because you're going to square it, so you get 0.095. And then that basically means that what you have here is that the Poynting vector at this time, S max times cosine squared of omega t, becomes 1.66 times 10 to the whatever it was, 15. Scroll up here and find it. 10 to the 14 watts per meter squared times cosine squared of 9.42 times 0.2. And this term right here is 0.09549. And so you end up with S is equal to that times the 1.66 times 10 to the 14. And so you get 1.585, so 1.59 times 10 to the 13 watts per meter squared. And so that is what the intensity of this electromagnetic radiation is 2 femtoseconds after the peak intensity has passed. Okay, now let's look at a different set of short examples. So that first set of examples was to go through some basic energy and intensity calculations. Now let's do some force and momentum calculations. So you have a laser. You're given the average intensity 444 megawatts per square centimeter. And it wants to know what's the pressure which this laser exerts on its target under 3 different conditions. The first one is that you have a laser beam dump. That's what's shown in this picture here. The second is it's reflecting back off of a mirror. And the third one is that you have a piece of glass which transmits twice as much energy as it reflects. So basically you have 3 cases: total absorption, total reflection, partial absorption, partial reflection. We're going to assume, by the way, that the transmitted energy all ends up being absorbed by the piece of glass, for example. It's also possible to transmit energy in such a way that almost none of it gets absorbed by the piece of glass. So we'll assume that it's like opaque glass and eventually the light is absorbed. So the average pressure when absorbed, so for A, it would be P is the average of the Poynting vector divided by C. Well, that's also the average of the intensity divided by C. So 444 megawatts per centimeter squared divided by 3.00 times 10 to the 8 meters per second. So we're probably going to need to convert this guy into how many megawatts per meter squared. So a megawatt is 10 to the 6th, and there are 10 to the 4 meters, centimeters squared in a meter squared. So this is basically 444 times 10 to the 10th watts per meter squared divided by 3.00 times 10 to the 8 meters per second squared. Okay, so in this case, you have a pressure of 444 divided by 3, which is 148. So 148 times 10 squared watts per meter squared over meters per second squared gives you newtons per meter. So we'll just put that in proper scientific notation. 1.48 times 10 to the 4 newtons per meter squared is the pressure that we would be getting for the absorbed case. In the reflected case, the amount of momentum is doubled and hence the pressure is also doubled. So you use 2s over c. And so in this case, we should be getting 2.96 times 10 to the 4 newtons per meter squared. Okay, for part C, we have that the glass transmits twice as much energy as it reflects. There's really two ways that you can deal with the transmission. One is to say that the glass is opaque and therefore this is being ultimately absorbed. The other is to say that no, the glass is transparent and so this is ultimately being transmitted. And in fact, a slightly more advanced example would say, well, neither one is quite true. The light is being partially attenuated and therefore partially absorbed. I'm going to work the two simple versions. So version 1 of C, C1, is that we have 2/3 absorbed and 1/3 reflected. And in fact, let's go ahead and say that there is a total pressure, P total, which is equal to P1 plus P2. So P1 is due to the absorbed part, P2 is due to the reflected part. Okay, so P1 should be effectively, we could call it S1 over C, where S1 is actually 2/3 of S. So we would have 2/3 of S over C. So that's 2 times basically 4.44 times 10 to the 12 watts per meter squared. And then that is going to be divided by 3 times 3 by 10 to the 8 meters per second. And so P1 is going to be given by about 9.86666 repeating, so 9.87 times 10 to the 3 newtons per meter squared. P2 for its part should be 2 times S2 over C, and so that is 2 times 1/3 of S over C, and so that's the same thing that we got for P1. So 9.87 times 10 to the 3 newtons per meter squared. And so P total is the sum of these two guys is going to look like basically 9.87 times 2 times 10 to the 3. So if we multiply this 9.87 times 2, you end up getting 1.97 times 10 to the 4 newtons per meter squared. So now the question is, does this actually make sense? And the answer is yes, because what we expect is to have a total pressure here that is greater than the pressure that you'd get if everything was just absorbed, but less than the pressure that you'd get if everything was reflected. And that is, in fact, what we seem to be seeing. In fact, it's about a third of the way between this pressure and this pressure, the absorbed pressure and the reflected pressure. The other way to approach this would be to say, instead of having 2/3 absorbed and 1/3 reflected, what if 2/3 is truly transmitted, so no absorption, no reflection, and 1/3 is reflected? Well, if that happens, then this pressure P2 actually is 0, because the photons pass through the object and therefore they continue to carry whatever momentum they started with. And so therefore the total would just be due to P2, which we found up here was 9.87 times 10 to the 3 newtons per meter squared. So you can imagine that there is a sort of third scenario in which a third gets reflected, 2/3 is transmitted through the interface, and then there's some attenuation factor, and the question becomes, given the attenuation factor and the depth of the glass, what is the total pressure going to be? I'm not going to do that particular example right now because it would be a very long example to add to an already fairly long video. So I want to do the next example, which is, if the laser has a spot radius of 5 millimeters, how much force is it actually exerting in each of the above cases? Well, force is given by pressure times area. And the area is going to be pi times the radius squared. So since the radius is given by 5 millimeters, 5.00 millimeters, that means that it is in fact 5 times 10 to the minus 3 meters. So the area, therefore, is going to be 25 times pi times 10 to the minus 6. So that's basically going to be 7.85 times 10 to the minus 5 square meters. So now we can multiply each of these pressures. So we have this pressure, we have this pressure, and we had this pressure for the totally reflected case. So basically we have A, the force is going to be 1.48 times 10 to the 4 newtons per meter squared, and that's multiplied by 7.85 times 10 to the minus 5 meters squared. And so the force when it's totally reflected, therefore, is going to be something like 1.16 newtons. Sorry, that is when it is all absorbed, not all reflected. In case B, if it's all reflected, the force should be twice as much, and so you should get 2.32 newtons. So that's all reflected. In case C, we had this one in which you got 1.97 times 10 to the 4. So 1.97 times 7.85 0.85 gives us 15.46, and that's times 10 to the 4 times 10 to the minus 5. So force for case 1 is going to be 1.54 newtons, and for case 2 it's going to be given by only half of that. So half of that would be 0.773 newtons. So that's how much force this laser is exerting on the object in each of these three cases. Now note that this is certainly a measurable amount of force in each case. For example, if you attached whatever this object is to the back of, let's say, like a sail, maybe it acts as a sail on the back of a car, like a small cart that could roll. In each one of these cases, as long as the cart is on a flat ground and as long as it has wheels that allow it to roll, you'd be able to see as this laser hits the mirror that the cart would start accelerating. Now with that said, this is a fairly high intensity laser. 444 megawatts per centimeter squared as a CW laser source is actually very, very powerful. It would in fact probably exceed most CW laser sources available. CW means continuous wave. Usually you use a pulsed laser to obtain that kind of power, and a pulsed laser has a much shorter pulse duration, although you maybe will have multiple pulses per second. But this is a measurable amount of force, is the point here. So that brings me to the end of today's lecture and of this lecture set. And so there was quite a bit of short examples. I don't have any long example that I want to work out. But hopefully you enjoyed this lecture. It is, in fact, sort of the traditional last lecture of the topic of electromagnetism. The next topic that usually gets covered in a physics sequence is something like optics, although in some sequences that gets covered first somehow and then you go on to modern physics after this. So that is it for today, and hope you enjoyed this last video, and thanks for watching.